So welcome to the next session. It's I guess it's like the first morning session of today, of Wednesday, and this is session on data structures and algorithms, and mostly. And the first talk is going to be given by Bryce Sandlund from University of Waterloo, and it's a paper together with Sebastian Wild from University of Liverpool, and he's going to talk about lazy search trees. So please go ahead.
Hi guys, as you know, I'm Bryce Sandlund from Waterloo, and our talk is Lazy Search Trees, joint work with Sebastian Wild from Liverpool. All right, so what is the problem description? So basically, we're going to try to support any operation that is computable on a binary search tree. I have a set of queries listed here, as well as a set of updates. And just a quick note, this merge is going to be as in binary search tree merge, where T1 has elements that are all smaller than or equal to T2. And we're going to go ahead and call this the sorted dictionary problem. And the reason we're doing this is just because the standard dictionary problem, which is just to support insert, delete, and membership queries, well, you don't really need to maintain order. And so you can actually just solve that problem in practice. You're just going to use a hash table and support these operations in constant time. Okay, so what are the existing sorted dictionaries? They're just all balanced binary search trees. I just have a few of them listed here, but they give you log n time per operation. However, there are some strong guarantees if you use, for example, a splay tree. And so I've got a few of them listed below, these stronger performance guarantees. And that really the big thing here is something called the dynamic optimality conjecture. Many of you probably are familiar with it, but it conjectures that the splay tree is constant competitive with any other binary search tree on any sufficiently long access sequence. And this has received a lot of attention since it was originally proposed in 1985. You can see some of the most important publications in this line of work listed here, and it continues to see actually quite a lot of treatment in some of the most important theoretical computer science venues. And so this is a motivating question for our work, and the idea here is so we're considering the best binary search tree and trying to get these really tight bounds on individual access sequences. But in some sense, this is already artificially restrictive in the design space. There's no particular reason, if we're consuming this data structure, that we should require it be a binary search tree. And if we instead allow different pointer-based data structures, we can perhaps get additional optimization. And we would be able to get perhaps better insert or better query operations rather than just the standard access, which is considered in dynamic optimality literature. And in line with this motivation, we have a strong theory of efficient priority queues, and it shows that Fibonacci heaps and related priority queues can offer improved runtimes if we restrict the operation set. So in particular, if our queries are only for the extrema, for minimum and maximum, well, then we can support insert in constant time. We can support a dubious key in constant time. And we can go ahead and make this merge just in arbitrary merge and also support it in constant time. So the idea here is it might be possible to actually reap some of these benefits on a data structure that supports even the operations here, just because yeah, we might be able to kind of generalize priority queues and take some of this benefit into the binary search tree type data structures. Okay, so what is the related work in this line of thinking? Well, it hasn't really been focused on too thoroughly, but there's a couple areas that touch it in some way. So the first of this is deferred data structures, and this shows you can answer Q queries on a static set of n unsorted elements in about n log Q plus Q log n time. And you could go ahead and make this dynamic in some sense by adding insertions and deletions in this Q prime metric, and then you get n log Q prime plus Q prime log n. Another related area is multiple selection. I'll talk more about this in the rest of the talk, but multiple selection problem, it's simple. You're just given n elements, and you want to find the element of rank R1, R2, all the way to RQ for some set of ranks, R1 to RQ. And there's both a lower bound and a matching upper bound is this measure B here. And I'll explain that a little bit later, but B is some measure that takes into account the specific query ranks. And so you can go ahead and answer the multiple selection problem online in any order, still in optimal time. And there's also dynamic versions of multiple selection that have been studied. And you get something similar to what's been done in this deferred data structuring literature. Now, we're going to try to look for stuff we're looking for tighter optimization than what this existing literature provides. So specifically in deferred data structures, we're not considering query ranks at all. And so we get this n log q. Well, we're trying to actually generalize efficient priority queues. So a Fibonacci heap can answer n insertions and q extract minimums in O of n plus q log n, which is a lot better than n log q. So we're going to try to do better than this. And then similarly, in these models that do have some form of dynamism supported, we've coupled the queries and insertions. So this really does not become, it's only meaningful if the number of initial elements is quite large. As soon as your number of insertions become linear, then this is just going to be n log n. It's no different than a balanced binary search tree. Okay, so what is our model? I'll explain the actual results that we get actually at the end of the talk, which is a little unusual, but I need to explain our model first in order for those results to make sense. So we're going to operate where we store the elements of our data structure in this kind of semi-sorted order, where we have these set of gaps such that each of the gaps individually are unsorted, but respectively, they satisfy a linear order, total order, so that, for example, all the elements in delta 1 are less than or equal to all the elements in delta 2. And we can support dynamic operations intuitively. If we're inserting an element, we just put it in the proper place, not too difficult. Now, queries are going to be kind of interesting, and we'll see how this corresponds to actually multiple selection in a little bit here. But a query is going to actually fall in a particular gap and split the gap into two new gaps in a rank R associated with the query operation. So say, for example, my query is I want to determine the rank of 5, which is the number of elements less than or equal to 5 stored in my data structure. Well, then the answer to this is actually going to be 9. And this will be the rank I associate with the query operation. I've partitioned my gap delta 2 around the elements less than or equal to 5 and the elements greater than 5, correspondingly the elements of rank less than 9, the elements of rank more than 9. And then we split the gap and end up with two new gaps as such. Okay, how am I going to choose this rank R? Very intuitive. It's roughly the idea here is I need to find where in my sequence I need to sort. What do I need to actually determine specifically in order to answer the queries? And so it's roughly intuitive with what the operation is. Basically, just that point I need to recurse into. Okay, so like I said, multiple selection. So multiple selection problem could, for example, ask for the elements of rank 3 and the elements of rank 9, so the third smallest element, the ninth smallest element. In which case, I end up dividing my elements based on these two ranks into what will be 3 gaps that I have listed here. Similarly, you can actually get binary search trees from our model, and that just corresponds to each element having its own gap. And we're going to actually see that priority queues will correspond to a single gap delta 1. Extract minimums. I'll work as follows. I have a minimum query. My rank R is 1. I separate it out into its own gap. And then I extract the minimum and remove the gap. I'm back to a single gap. Okay, so rough idea here. We're going to come back to this measure B that's used in this multiple selection literature. And it's actually going to characterize the amount of work or the information present in the current gap partition. So clearly, in order to sort the whole sequence, this is going to be n log n time. That's a tight bound for multiple selection, and sorting. If I have only one gap, I have no information stored at all, b equals 0. And then in general, I'm going to get that B is going to be n log Q. So we're seeing this n log Q term coming back organically in our model. And yeah, so our complexity is going to be roughly, we want to achieve this optimal B plus N time, similar to multiple selection literature. So I need to look at the specific bounds that will be required for insertion and for queries. And so for insertion, we have just a lemma here that it's going to be this log N over delta I. And this is good because we can just store each of the gaps in a biased search tree. And then we get that the access to a gap delta I takes this log N over delta I time exactly as intended. Now, queries are going to boil down to splitting a particular gap. We can show that we'll answer the query in time corresponding to the split. And so I've notated this such that if the two resulting gaps are of size X is the smaller one and CX is the larger one, then the complexity of doing this is going to be omega X log C. At least that's the lower bound. And so, yeah, we can go ahead and look and see how this will end up. We'll actually get the priority queue runtimes organically from our model. So if we have only one gap delta 1, then insertions takes this log N over cardinally delta 1. This is just constant time. Similarly, removal of the minimum is going to have X equal 1. C is going to be theta N. So this X log C is now just log N. So this is exactly what the theory of efficient priority queues has shown is the correct runtimes to be optimal. Now, in order to actually split these gaps in this O of X log C time, it's going to be the main technical part of our work. I don't want to go into the details because it's too technical. But yeah, unfortunately, the way we do this, we add log N to our insertion time. So we'll go ahead and just give our results here now. So instead of achieving this B exactly over a series of N insertions, Q unit queries, we get this B plus these little terms, close to optimal, but not quite. Some extra couple things our data structure does. Only uses Q or N, O of Q or N pointers. It's a lot better than a binary search tree, which uses 2N at least. And so this is probably going to provide a little bit extra optimization. We can also get the efficient access efficient access properties of display tree. We can just achieve those automatically, which is kind of interesting. So the applications, instead of getting N log N time on a series of N insertions and Q queries, we get N log Q plus Q log N. This is similar to the related work, but we've generalized it further. Insertions and queries are not coupled. And then if we do actually have a non-uniform access sequence, for example, if I have N insertions and Q over K queries for K consecutive keys, I get this interesting runtime where essentially this N log Q is probably a dominating term. So now it's N log Q over K. So I get the K consecutive keys essentially for free, which is kind of interesting. Just a few other applications here. I don't have to go into particular detail about them, but you can see them, and if you'd like to read the paper, then I suggest you do so.
Okay, thank you very much. So are there questions? So I have a question. So you mentioned actually dynamic optimality and that you don't have to actually stick to trees. So what kind of model do you actually use? Do you use RAM, or can you implement it on pointer machine, or what kind of?
Yeah, we don't need word RAM. We do suggest using arrays because then you can get that pointer bound. But yeah, we don't need constant time access to memory locations, so we can just use the pointer machine.
I see.
Can I ask a question?
Yeah.
Yep. Go ahead.
So why did you choose as a title lazy trees when, what I understand, you don't want to use trees anyway?
So the reason we call it lazy search trees is that we do use a biased search tree at the top level data structure. So we really are still using binary search trees. It's just that we're just taking the rough idea of there's no reason to sort on insert. And if you delay sorting until you actually answer queries, then you can get these fine-grained runtimes that are slightly better than what a binary search tree gives.
Is it maybe more of a bush than a tree, or if you're not sorting?
More of a what's that?
Oh, sorry. My English is not my native language. Bush, I think, is you say it in English. Is a plant that is not as tall as a tree.
More of a bush than a tree. Yeah, sure. I guess that you could consider that.
Okay. Well, thank you very much for the talk. We need to move to the next talk. So the next talk is going to be given by Pingang Cheng, and he's going to talk about today fractional cascading, and it's a joint work with Peyman Afshahani. Please go ahead.
Yeah, can you hear me? Yeah. Yeah, this talk is about 2D fractional cascading on axis-aligned planar subdivisions. My name is Pian Chen, and this is a joint work with Peyman Afshahani, and we are from Aarhus University. So, today I will first introduce the background of this problem, and then I will present you our results, and then finally I will talk a little bit about the applications and open problems. So first, background. Fractional cascading is a data structure technique used to solve the iterative search problem. And in this problem, we are, so the input of this problem is an underlying graph, G, which is degree bounded. And for each vertex of this graph, we associate it with a set of values from a totally ordered universe, U. And the query is given by a connected subgraph and also a query element. So for example, here, all those orange edges describe the query subgraph, and we have a query element Q, which is 24. So what we want is to find the predecessors of these query elements in the sets associated with the vertices of this query subgraph. So here, all those red edges are just the output of this query. So to solve this problem, a trivial solution is to just build the optimal predecessor searching data structure for each node individually. So if we have a path of length pi, then we need to do pi many individual predecessor searching, and each of them take log n time. So in total, we solve this problem using order pi times log n time, and clearly it takes order n space. But the result of Chazelle and Guibas in 1986 is very surprising. They invented something called fractional cascading, which tells us that using linear space, we can actually do much better. We can solve this problem using order pi plus log n time. And now what we want to do is to generalize this problem. So first, let's look at what we are actually doing for each node. We want to find the predecessor of some query elements in the set. And this is actually one point location problem. So suppose we have a real line and we put the elements of this set S to this real line. So we will divide this real line into several disjoint regions, and to find the predecessor of a query element in the set is equivalent to locate the range which contains the query elements. So there exists optimal one-to-point location data structures that can solve this problem using linear space and order log n query time. And n is total number of ranges, which is also the total number of elements in the set S. And a very natural generalization is a 2D point location problem. So here we're given a planar subdivision, and we want to locate the points in the subdivision, which is we want to find the face containing the query elements. So recall that planar subdivision is just an embedding of planar graph in 2D plane, where all edges are just straight line segments. So a very simple example here is, so the left bottom is just a planar subdivision, and we want to find the cell containing the red query points. And we also can solve this problem using optimal 2D point location data structure using linear space and order log n query time. And here n is the total number of vertices, edges, and faces in the subdivision. So now we can try to generalize fractional cascading to 2D. So again, we have underlying graph, which is degree bounded. And this time, instead of associate a set of elements to each node, we associate a planar subdivision to each node. And the query is also given by a connected subgraph and also query elements. And this time it will be a 2D point, of course. So we want to find all the cells containing the query elements in the vertices of the query subgraph. So let n be the complexity of subdivisions associated with G. Remember, that's just the total number of vertices, edges, and faces in the problem. So a trivial solution, again, we can build optimal point location data structures for each subdivision individually. And it will, of course, give us the order pi times log n query time and linear space. So what we want to ask is, can we do better? Sadly, the answer is no. By the result of Chazelle and Liu in 2001, any data structure solving this problem using polylogarithmic plus little of pi times log n time must use tilde omega n to 2 minus epsilon space. So essentially, the trivial solution is the best we can hope for. And the bad example they give is also very surprising. It's very simple. We just have a path, and we associate every node of this path with a subdivision, where every cell is just a parallel line, parallel strips, and it will break everything. So in this paper, we consider a very special planar subdivision, which is axis-aligned planar subdivision. So in this setting, all the edges will be parallel to the x or y axis. So can we do better in this special type of subdivisions? We show that, yes, we do. So now I will show you our results. So we consider not just the case when the underlying graph is a graph, we also consider the case when the underlying graph is a tree. We also consider path queries, subtree queries, and also the more general subgraph queries. We obtained a bunch of upper bounds and lower bounds, and some of our upper bounds matches our lower bound. And for some, they almost match the lower bound up to some tiny inverse argument function factor. So as you can see, our result is always better than the trivial solution by a square root log n factor. And for some cases of the path query of cheese, we can actually achieve better results. So let's first look at the first two rows. There are several terms in the upper bound. Let's look at one by one. So first, the pi times square root log n term. It actually corresponds to the case when the height of the tree is bounded by half log n. So in this case, we can show that there exists a data structure solving the path query on trees problem using order log n plus pi times square root log n time using order n space. And we can show a matching lower bound for this. And so this is tight. And for the second term, it actually corresponds to the case when the height of the tree is between half log n and half log n squared. And we want to solve root leaf query, then we can show that there exists a data structure solving this problem using order log n plus square root pi times log n time. And the space usage is also linear. And since for now we only support root leaf queries, if we want to support arbitrary length path queries, we need some more ideas. And that's the reason why we have this inverse argument function factor in our results. But for this root leaf query, we can show that this is also tight. So for the two branches in the minimum, our results are tight. And the last term is actually a simple case when the height of the tree is more than half log n squared. So in this case, we can use some very simple technique. We can just use heavy path decomposition, and we can solve the query for long path in order pi time and order n space. And we can, and this of course tight. And for the last two rows, actually, for a subtree query of trees, we can actually transform this to subgraph query of graphs. And subgraph query on graphs can again be transformed to path query on graphs. And as you can see here, actually, the last two rows share some terms with the first two rows. And this is actually because they use the same data structure. And again, we can show this is tight. So finally, I want to talk a bit about the applications and open problems. So the first application is GI system. So in such systems, we usually have a map, which describes several different features of a given region. And such a map usually consists of a series of maps, and each of them describing one specific feature of that region. So if we want to do point location in the map, usually corresponds to do repeated point locations. So in some cases, our solutions can be used to help improve the efficiency of such systems. And another application is orthogonal range searching in higher dimensions. Actually, in such problems, we usually need to solve a problem which corresponds to the tree path, the path query on trees. Actually, one of the motivations of our paper is from 4D dominance query. Now I want to talk about the open problems. The first open problem is 3D generalization. It's actually not easy to generalize our results to 3D because we use some techniques like trapezoid decomposition and orthogonal point location. We can have optimal solutions for them in 2D, but for 3D, we don't know optimal solutions yet. So it's quite challenging. Also, we can consider some more special settings. In our setting, we only restrict that the total number of planar subdivision complexity is order n, but we can restrict, for example, the complexity, the planar subdivision complexity of each node is within some constant factor of each other. So in this case, we think we can achieve better results. And finally, we can also consider dynamization and other computational models as well. Yeah, that's my talk. Thank you. Any questions? Sorry, you're muted, I think.
Yes. So, sorry, yes.
Yeah.
Thank you very much. Questions? So in 3D, you mentioned that that actually you are working on it, but do you have any improvement actually over trivial solutions or axis aligned stuff, or not actually, not at all?
Yeah, for the general 2D fractional cascading, basically the lower bound of Chazelle and Liu show that we cannot improve too much. Basically, the trivial solution is the best. But for us, our lower bound is pi times square root log n. So the trivial is pi times log n. So we improve the trivial by a square root log n factor. So
right, but well, you mentioned this 3D, but can you actually do like a little bit in the 3D or not at all actually? Not in 2D, but in 3D actually. So you mentioned it.
Well, in 3D,
can you get any improvement actually?
Yeah, maybe we can improve that a bit. The thing is, for trapezoid decomposition in 2D, if we have a subdivision of order n complexity, trapezoid decomposition can, can decompose the graph and also have the same complexity. But for 3D, that's not true. So the complexity of the subdivision increases. But for 3D orthogonal range point location, we can achieve optimal, but that's not a pure point machine model. There's actually a paper this year, I think, we can achieve order log n query time at order n space, but that's augmented point location point machine model. So I think we can improve something, but not in the pure point machine model.
I see. Questions? Okay, well, if there are no other questions, then let me thank the speaker again. And thank you. And let's actually prepare for the next talk. So that's going to be given, I guess, by who? Who is the speaker actually? Jakob or?
Me? I'll give the talk.
Oh, okay. So you will be giving the talk. Okay. Is that Thomas Allen?
Yeah, Thomas Allen. Yeah.
Okay, good. So the next talk is going to be given by Thomas Ale, and it's about hashing-based set similarity search, and it's a joint paper with Jakob Knudsen.
Thank you. Oops, wait. I forgot how do you do the screen sharing thing?
There's a button at the bottom, green button.
Oh yes, of course, it's the big green one. Okay. So yes. Can you all see it now?
Yes, you can
Okay.
see.
Yes. Great. So yeah, but thank you all for tuning into my talk on subsets and supermajorities, together with Jakob Knudsen, who's in the chat. If you have any questions as we go along. So probably your first question would be, what is similarity search? And what is this problem we're solving? So basically, you're given a database of sets. So in this case, the sets are all the black circles. And it can be from any kind of universe that you can think of. Like it could be like documents or movies or something. Or, and then you have to pre-process all these sets. So when we bring in some query, then you can efficiently find the ones that are similar to your sets. In this case, the green one, you can see maybe probably it's more similar to the one that it overlaps with. So this problem in general for high dimensions, like all these search problems, they're OVP hard, so you can't really do better than searching through everything in your database. So we study like an approximate version where you assume that the sets that you're not interested in finding, they're also like there's some gap, so the similarity is somewhat smaller. And one way to formalize this is to assume that all the sets you're not interested in are somehow generated like independently from your query. So it's like there's like a planted good set you're looking for, and everything else is kind of random. Okay, so the second question you might be interested in is what exactly do I mean by similarity? And people have studied this problem under a lot of different measures of similarity. Like back in '98, there was this min-hash algorithm, which started a lot of this LSH, locality-sensitive hashing, which uses something called Shakard similarity. And there's been a lot of work in making data structures for data that sort of can be seen as a vector on the sphere and Hamming space or something, and you can also map sets into these spaces, and you end up getting some similarity measure on sets. There's a famous hyperplane hashing algorithm, which does sort of angular distance, and recently there was something called chosen path, which works if you're interested in something called brown blanket similarity. But basically, I think this is getting a bit out of hand, and there are a lot of measures we don't know about. Like I really like this survey on binary similarity distance measures, which just has like hundreds of different ways you can measure similarity of sets, and they even have these graphs that show like how similar are these different measures on similar things. So what we're interested in now is in this paper is about generalizing this notion and trying to come up with an algorithm that's optimal across all of these hundreds of different measures. And the first simple observation for this is that we can reduce basically any similarity measure on sets because they're sort of symmetric. If we only know the size of the sets, the query set and the size of the sets in the database, then all the set similarity measures just turned into some notion of set overlap. And we can reduce to this case by making multiple data structures, like a logarithmic number of them, where we store the small sets and the slightly bigger sets and so on. And then we just query each data structure where we compute what should the overlap be given this similarity measure in this database and so on. So this is what we do. And then we solve this problem we call WQ, WU, W1, W2 set similarity search, which is the version where you know the size of the query, you know the size of the other sets, and you know you have a particular overlap you're looking for, and you assume that the other things have a smaller overlap, W2. And we managed to find a very general algorithm for this problem that is optimal over nearly all of these parameters. Yeah, at least where there's this small caveat, like usually, like we only know for any of these kind of data structures to show optimality results in this case where where this sort of random case, as I talked about, where the W2 is equal to sort of the like you assume that everything else just has an overlap, which is what you would expect if you'd sampled a set at random of that size. Okay, so quickly to understand the algorithm, the idea is that we have a lot of lists you see out in the side, 1, 2, 3, 4, and so on. And we then sample these very small blue circle sets. And every of the big sets, if it has a big enough overlap, what we say a supermajority of this small representative set, if that's inside the big set, then it goes in that list. So for example, A, you see it goes into list 5 because it completely contains the small blue circle 5, but it also goes into list 1 because it just contains most of the representative 5. And then to query the data structure, we look at which of these small blue sets are inside the query. And in this case, it's also 1 that has a big overlap with that. So then we look in list 1 and we see, okay, there was A. And then we compute the actual similarity with A. And if that's big enough, then we return that. And if you analyze on this, and you also need to set these thresholds very finely, like how much do you require from the queries, how much do you require from the other things, and a ton of things you can balance out. But yeah, wait, I want to show you, I don't think I'll have time for this lower bound. I was hoping I had, but I want to show you this instead. So the main problem now with this algorithm is that how many of these lists do we need? We end up needing a super polynomial amount, something like n to the log n, many lists. So it's completely impossible to go through every single one. Instead, we want to generate them in a more structured manner. So we start out by just picking, like in this case, if this on the left side here, it's our universe, and all the blue ones, yeah, let's not think about the blue ones for now. we pick a number of random elements from the universe, and then for each of those, we expand it, like we grow it, and then we pick new elements like this. So we sort of grow a lot of these small sets in a tree-like manner. And the nice thing about this is that then if we're only interested in the ones that eventually have a very big overlap with our query, then we can, as it happened here a moment ago before, we get rid of all the ones that are unlikely to ever capture a lot of like our blue elements. And so we sort of get this branching random process that we can repeat, and that it ends up generating something that's very close to a uniform big set of these small blue sets, but for which we only really need to pay for the ones that that we end up using. Yeah, and that's probably what I had time for, but you can see the rest in the long video, and then we have like a very nice lower bound for this thing, because we don't actually end up getting a constructive bound. Like we can't say exactly how good our algorithm is. We can just say that given our algorithm gives a certain value, we can then transform that back into a lower bound to say that no other algorithm can do better than this.
Okay. Thank you. Thank you for your talk. Other questions? So you mentioned that actually you need like a super polynomial like number of these seed sets. So I didn't quite understand. So how do you actually get rid of why don't you have to generate all of them actually?
Yes. So the intuition is that let's say that say we're only interested in the ones that have 70 where 70% of the elements in them are in some particular set. Like now I have this set and I want to know which lists does this correspond to. So then when I start building these things and I build them iteratively, then if I have one of them and I have already sampled 3 elements from the universe, but none of them are inside my big set, then I kind of just assume that probably this one is never going to work. It's sort of, whereas I can, if I look the other way back and I sort of condition on this thing ending up, like eventually this being a useful one, then it's also going to be useful like at all the time steps until we go, as we go up.
Okay.
And yeah, I think also part of one of the difficult parts is then that once you then change to this tree view, you have to consider what happens for if you're decoding 2 sets at the same time. So you have one set for your query, and then you also want to know what happens with the one in your database that you're looking for, and you need to track that neither of them, like both, this representative has to keep being good for both of them all the time slots as you go down. Yeah. Oh yeah, and if there's more time, then I can have this. This is a plot of the.
You have like 4 minutes, yeah. So what is the plot showing actually?
Yeah, so the x-axis is the exponent of the query time. So where it says 0.1, it means that the query time is n to the 0.1, and n is the number of sets in the database. And the y-axis is the exponent of the space, or actually you have to add 1. So where it says, you can, for example, see that if we use slightly less than n to the 1.3, then we can get nearly constant query time. And you can see, so there was some previous work that also had these space-time trade-offs, the spherical LSF. But if you try to solve these sort of set problems with it, it doesn't work very well, even though it's optimal for spherical data. And there are some of these other min-hash and chosen path algorithms that they always have like this sort of balanced space and time usage. But we still beat them, like if we go to our sort of our own balanced view.
So you mentioned some lower bounds. So these lower bounds actually are for your approach, or actually for like general?
Yeah. So these lower bounds are for this very general type of data structure, LSA data structure, called the list of point data structure. So you could say in a sense it's for our approach, but where you can sort of pick any kind of policy for how to make these lists. So all these other algorithms, you can look at them in the same way, but they have different policy for when something goes in a list. But our lower bound also holds for cell probe. Like we can sort of plug into, like our lower bound sort of generates kind of inequality that also gives you 1 and 2 cell probe lower bounds. So for very, so down here for the very small query times, this space that we use, it's also, you can show that this is also necessary space for 2 cell probe data structure.
And your lower bounds actually match your approach, or are they slightly weaker, or actually?
Yeah, so they match up to like lower order terms. So we're mostly interested in finding the best exponent on n, but there's some n to the like square root log n or something. No, 1 over square root log n. Yeah, some n to the small o of 1. Which would be interesting probably to get rid of. I think we have something like log n to the 27 or something in front, because we didn't really try and optimize it. And at some point we had a competition with somebody else who said he had an algorithm with 100 log n's, maybe 4. We didn't manage to get that.
Okay, are there questions? Well, if not, then thanks the speaker. Thank you. And let's go to the next talk, and that's going to be given by Gleb Posobin. So can you share the screen?
Yep. Can you see it? Yeah.
So Galap is going to talk about the data structural error bounds in the group model, and it's joint work with Alexander Golovnev, Oded Degev, and Omri Weinstein.
Thank you for the introduction. Like our paper is called Data Structural Error Bounds in the Group Model. First, quick refresher on the self-probe model and group model for data structures. The data structures looks as follows. We have n objects, and they can be like edges in a sparse graph, or they can be like points, and it can be points on a plane or in d-dimensional space. And we're asked to preprocess them with and take however long we want to preprocess them into as memory cells, where memory cells can contain, for example, bit strings of fixed lengths or group elements. For the group model, those would be group elements. And then based on those as memory cells, we need to be able to, the data structure needs to be able to respond to m possible queries. And each query has to be answered by looking only at most T cells. And it can be done either adaptively and not adaptively, like to different variations. The function that computes the output of the query can be arbitrary in the cell probe model. That's the basic formulation of the data structure model. And we will be looking at the group model, where the elements stored in the memory cells have to be elements of some abelian group, and the outputs can be combined. They can be combined to obtain the outputs by adding or subtracting the memory cells. But again, the same restrictions now that there are only T memory cells can be read. And we say that the data structure is efficient if the space used is linear in the number of input points and the time is polylogarithmic. The query time is polylogarithmic. So the lower bounds that we'll show is for the range counting with weights problem. So the input, the n input points are just points on a two-dimensional plane, and each one has an assigned weight from some abelian group. For us, it would be a group CP for some large enough P, and the ranges. Like there are different variations of what ranges can you allow. Can one allow the one natural one is, for example, axis-aligned rectangles, and we will be looking at more general form of that. We'll be looking at convex polygons in the plane, and so the query that comes is the convex polygon, and we need to return the sum of the weights for the points that fall inside this polygon. So if we, here for this triangle, the answer would be 8. The sum of the points inside this triangle is 8. For this rectangle, the answer would be 9. So the natural measure of complexity of those ranges can be taken as the complexity of the system of inequalities that describe this range for this family of ranges, for example. And for the this range counting problem is very natural to look at it in the group model, because the best known upper bounds for it only use some subtract and add the weights, exactly those operations that a group model provides, and they don't multiply, like, for example, range trees don't multiply the weights by numbers, or don't do anything more fancy than adding or subtracting them. So the previous there were no known superlogarithmic lower bounds previously for the group model, and also, of course, for the self-group model, linear model. There are, on the other hand, there are known lower bounds that match the upper bounds for even more restricted version of the group model called semi-group model, which was obtained in the 80s. So this is like the overview of where those stands, and so our result looks as follows. we show an explicit range counting problem in 2 dimensions with n-cubed queries, such that any data structure in the group model with linear space must have the time n to the omega of 1, the query time. And our proof proceeds in 5 steps. The first step was we showed that the outputs of any efficient data structure cannot be diverse, where diverse is like a property that I won't give a definition now, won't have time. But so the outputs of any efficient data structure do not have this property as long as there's enough queries, like n-cubed queries suffices. And if the efficient data structure if the data structure is efficient, the outputs are not diverse. Then we show that if the incidence matrix of a range counting problem satisfies the property known as k-wise independence for certain values of k, then it is possible to find the assignment of weights to the points such that the output has to be diverse. And so if such a range counting problem appears with such incidence matrix, we will know that it is not representable. We can't represent it by an efficient data structure. Then we show that k-wise independent matrices with parameters that are sufficient for us do exist, and in fact, random matrices are k-wise independent. Then we de-randomize this construction to use less randomness to be able to obtain a better range counting problem, a more natural version of range counting problem. And the last step is embedding this matrix that we obtain into 2 dimensions. So I'm not going to talk about the first step. I'll give a brief overview of the proof. First, about about the k-wise independence. Like the simple observation is that if we have the range counting problem, if you make a matrix M, where which is the incidence matrix of shapes to points, and multiply it by the weight vector W, weights of the points, then the resulting vector, the product is are all the possible answers to all the queries that you have, all the sums in the corresponding shapes of weights in the corresponding shapes. And so one idea is to assign weights double at random if you have the matrix M, and to see what happens then. If M were a square matrix, non-singular, then the M double would also be distributed uniformly at random, and it can be shown that this property that I haven't defined, diversity, would be satisfied for it with high probability. But M is not square; it is far from square for the first step in the proof, showing that the efficient data structure are not diverse. We need the M to be very tall. It needs to have n-cubed shapes, n-cubed rows, and columns. But it turns out that it's enough by version of Chernow bounds for k-wise independent variables for it to have independent rows. That is, any n over 100 rows have to be linearly independent. And if you are able to find such a binary matrix, then it is then MW will also be diverse with high probability. So now the question is whether we're able to find a range counting problem with a k-wise n over 100 wise independent incidence matrix. For that, first we need to show that such n over 100 wise independent matrices do exist. We do show that it turned out to be not a obvious result, but we're able to show it through anti-concentration inequalities, and namely the Littlewood-Offord lemma, which also in the later stage. So we're showing that just sampling uniformly random matrix gives a k-wise independent matrix, and the next step is de-randomizing this construction to use fewer random bits. In the proof, we're using only the anti-concentration equality bounding the probability that any given linear constraint is satisfied has to be not too large from Littlewood-Offord. And so we're basically using only that fact and the independence of the columns in the proof. So basically, we realized that it's enough for us to be able to not to increase not to increase this probability by too much. That is, if the random variables epsilon are generated from a pseudo-random source such that this probability doesn't increase much, then such a matrix would also work if the columns are generated not from uniformly random, but from this pseudo-random source. And such a pseudo-random source does exist. So Gopal and Ken and Mecca 2 years ago showed that there is a pseudo-random generator against hyperplanes and also half spaces, but also it's the same as pseudo-random generator against hyperplanes, which is seed length, which is log n times log n squared. And so now instead of generating random columns, we generate output. We generate a column as an output of the PRG on the random input, and the columns are still independent. So and the total number of random bits used is now much less than it was before. It was n to the fourth and log n. And now the last point is bending this into R2. This is a bit of a trick. Like it shows kind of that any problem, this way range counting problem can be embedded into two dimensions in the following way. You just put the points that you have on a circle and then connect the ones that you want to be inside one shape. So this way you get a nice convex polygon, and in the end you'll have a bunch of those convex polygons, and this will be your ranges in two dimensions. And if we do this according to the pseudo-random generator outputs, and the points correspond to the seeds for the pseudo-random generator, then all the previous results above show that we can find endpoints among those 2 to the r, where r is the seed length, such that the outputs of the pseudo-random generator are give a k-valence independent metrics, and so it is possible to find a setting of weights to them, such that the output of the data structure has to be diverse, and so the data structure to represent this set of polygons and this transfer queries for those points cannot be efficient. The only problem here, small problem caveat here, is that the number of sides of the polygons is large. It is 2 to the r, about 2 to the r, the number of points. And of course, it's going to improve as soon as someone comes up with a better pseudo-random generator against half spaces. So the number of sides will be 2 to the log n times log n squared. So this is the overview of the proof. Are there any questions? You're muted, sorry.
Sorry. Thank you very much. So, any questions? So I'm curious, actually. So if you would actually allow slightly bigger space, actually, is there some better solution known, or can you actually get something better for the range counting?
For the upper bound, you mean?
Yeah, for the upper bound. If you allow like superlinear space.
Yeah, about that I'm not sure. No. Yeah, I don't know that offhand. Yeah.
Okay. Other questions? If there are no more questions, then let's thank the speaker. Thank you. We will have next talk in 2 minutes, actually. So the next talk is going to be given by whom, actually? Is the speaker here? Is Omri here, or is Yang Kon Ko here?
Yes.
Oh, okay, you are here. So you are going to give the talk?
Yeah.
Excellent. Did you switch on the camera or not?
Let me just screen share.
Okay.
Yeah. So can you see the screen?
Yes, we can see the screen now.
Okay.
Okay. So let me introduce the next speaker, Yang Kun Ko. And this is a joint work with Omri Weinstein, and he's going to talk about adaptive step towards the multi-phase conjecture.
Okay, thank you.
Go ahead.
So the stop will be on the adaptive step towards the multi-phase conjecture. So obviously the next question is, what is multi-phase conjecture? So it concerns the dynamic data structure lower bound. In dynamic data structure, we have an online sequence of updates and query operations, and we want to cheaply maintain this sequence of operations by accessing our memory as little as possible. So for example, consider undirected graph connectivity, where the updates are insertion and deletion of edges, and you want to answer the following set of queries given any vertex S and T, are they connected or not? So for here, as in big picture, you are given a graph, you are allowed to add some edges. Now, given any set S and T, you have to be able to answer whether S and T are connected or not. Now, a naive data structure is to simply record all the updates in an adjacency matrix. And when given an S and T, just run PFS. This would result in one update time, because for every insertion or deletion, you're going to change one entry on the adjacency matrix, while the query time would be something like n. But you can also do something non-naive, non-trivial, is to maintain connected components instead in balanced tree, and this would result in log n update time and log n query time. Well, but unfortunately for directed graph, you cannot do such thing. So the question here is, what is the optimal trade-off between the update time and the query time? Now, the formal model for showing unconditional lower bound for the data structure is cell-probe model. Here, you're given a word size W, and you can view it as a sequence of these words of each of size W. Now, given such memory, you only measure the query complexity, i.e., the number of memory accesses that you're going to make to the data structure. All the computations are given for free. Now, in the context of the dynamic data structure, these measures how many cells you, during the update, you're allowed to read and write TU cells, while for the query, you're allowed to probe TQ cells. So for update 1, you write 119 here. For update 2, you'll able to write and then read and then change the entries. Now you'll do multiple updates, and at the given query, you'll be allowed to read TQ queries. Now we emphasize that this is an unconditional lower bound, as it's going to apply to any imaginable data structure, and it's a purely information theoretic lower bound. Now the goal here is to give a lower bound on TU and TQ simultaneously. Now, this model abstraction of the cell probe model comes at a price, making it notoriously difficult to obtain lower bounds. So proving an explicit lower bounds on TU and TQ is known to be very hard. And it's also noteworthy that conditional lower bounds is a different story. But for the past decades, there was a very slow progress on this lower bound frontier. In '89, there was the first near logarithmic bounds by Fredman and Sachs. In Petrascu and Demain, they proved the first logarithmic bound. And recently, there was this work by Larson et al., which proved log square bound. Now, in attempt to circumvent this limitation of techniques, Petrascu proposed the following online set disjointness problem as a candidate for proving the polynomial dynamic lower bounds, which it's sort of a holy grail. So in phase 1, you are given k collection of sets, and you're allowed to pre-process them in poly k time. In phase 2, a set T is revealed, and the data structure updates in T times TU, which is going to be O sub n times TU time. Then in phase 3, an index I is revealed, and the data structure must answer whether the set Si and T is disjoint or not after TQ queries. So in pictorially, consider the following sequence. So given the sets, you're allowed to pre-process in the memory. Now you're given the set T, you're allowed to update. Now given I, which is Si, you want to make TQ queries and determine whether Si and T are disjoint or not. Now, the multiphase conjecture by Petroscu states that either TU or TQ for this question must be some polynomial. And in fact, if you assume this conjecture, this has major implications to other dynamic probe algorithms, dynamic reachability, i.e. the directed version that I mentioned earlier, matrix vector multiplication, range code, etc., all takes polynomial time. But the progress on this question has been rather slow. So Petroscu showed that conditioned on the three-sum conjecture, the conjecture is true. But for unconditional lower bounds, there's a non-adaptive bound by Brody and Norton. So if you restrict to non-adaptive updates or non-adaptive queries, then you can show some polynomial bounds for actually other problems, not multi-phase problem. But if you are going to show full adaptive query bound, this is a different ballgame, and we're actually very far from proving the full conjecture. You can only show that for constant updates, polynomial query lower bounds. Now, we proved the theorem on the following very restrictive query model. On phase 1 and phase 2, we do not impose any restriction, but so you're given this now, but denote the updated cells as green cells. Then on query, we consider the following restriction, where given I, Si is free of charge. You're allowed to read T1s from the non-updated memory, and then you're allowed to read T2s from the updated memory. And we call this, so the data structure has an unbounded but layered adaptivity during the query stage. So you're allowed to alternate one time between the layers. And in fact, this generalizes all known set intersection upper bounds. And also, there is square root n upper bound, which is given by the Chattopadhyay et al. And the theorem is that any semi-adaptive data structure for multiphase, you need square root n queries or n update. So in other words, the upper bounds by the Chattopadhyay et al. Is actually optimal. Now, as a final remark, so I want to sort of mention why the progress on multiphase conjecture has been slow. So the Petroscu, in order to solve this conjecture, introduced the number on forehead communication game as a potential attack route for multiphase conjecture. So you're given Ellis, Bob, and Charlie. Ellis is given Si and I. Bob is given T and I, and Charlie is given S and T. Now, Charlie is allowed to give a private advice to Bob without knowing the index of the interesting subproblem. And then Ellis and Bob, they're allowed to communicate in the two-party manner. And the Petroscu conjecture that the short advice cannot help too much. And it's rather straightforward to see that the number on forward conjecture implies the multiphase conjecture because players can simulate the data structure. And now the intuition for this conjecture was the round elimination. If the advice is short, it cannot do much in the standard two-party communication. But it turns out that the Petrascu's number and Fourier conjecture is not ideal for proving multi-phase conjecture, in a sense that there is this connection between the number of Fourier conjecture to that of the circuit complexity of computing a linear operator. So to consider the following problem of designing a circuit with few wires for computing a given linear operator. So a counting argument shows that if one limits to linear gates, that is, the gates compute linear functions themselves, then for a random Boolean linear operator, the trivial circuit is near optimal. But the question remains, if we remove such restriction on the gates, i.e. if we allow arbitrary gates, can we prove a polynomial lower bound? Since the best known lower bound for this problem is slightly superlinear, and a major decades-old open problem is, can you show n to the 1 plus epsilon lower bounds for a random, even random matrix A? And in fact, we also showed that the Petrascu's number and Fourier conjecture actually implies a polynomial lower bounds for circuits with arbitrary gates computing a random linear operator. And we actually show that a cheap circuit implies too good to be true number and Fourier protocol, where Ellis is given a linear operator A, Bob is given X. So Ellis can therefore construct the circuit. Now Charlie, as advice, sends the contents of all high Fanning gates to Bob. And now with the high Fanning contents known, Ellis only needs few bits from Bob to compute AI times X. So the main message here is that the data structures are weaker than the general number on four-head model. And obviously the next open question is, can we actually prove the full multi-phase conjecture? Thank you.
Thank you. So are there questions? So I'm wondering actually. So you mentioned this this last connection between circuit level bounds and Petrascu problem. So you're saying basically like the Petrascu multiphase conjecture actually implies circuit level bounds. Now the question is actually, so there was this this paper by Untitled Chapter et al. And they actually show that this most general version of Petrascu conjecture is actually wrong. So what precisely actually does give you these level bounds, these circuit level bounds? What kind of Petrascu conjecture actually gives you the level bounds? So
I think the Chattopadhyay is a counterexample is actually not a linear operator. So
I see. So,
you want a linear operator. So here it's restricted to semi-ring model, but it's even open for like not even semi-rings, Boolean semi-rings, like F2, F finite, any finite field. So yeah.
So instead of taking set intersection, actually, you would just take basically like inner product of vectors. Is that right? Actually.
Yeah. So for inner product, recently there's this result by Bruno Loff and Pavel Dvorak, which shows that even for inner product, semi-adaptive data structure is optimal.
Right. Yeah. I see. Interesting. Are there other questions? Well, if not, let me thank the speaker. Thank you. And let's move to the last actually talk of this session, which is going to be given by Ariel Kulik. So Ariel Kulik will talk about two variable recurrence relations, and this is joint work with Hadas Shachnai. Ariel, you can go ahead.
Okay, can you hear me now?
Yeah, we can hear you now. Okay.
and K. So we're going to have some long introduction, after which we'll briefly go over the main results of the paper. And we're going to focus on vertex cover. So we start with the definition, which is that given an undirected graph G, we say that the subset S of vertices is a cover if for every edge U and V, there is a non-empty intersection between the set S and the endpoints U and V. So we have here a small graph as an example, and those two vertices form a cover. And this idea of vertex cover or a cover can be cast as an optimization problem in which we want to find a cover S of the graph G such that the number of vertices in S is minimal. And it can be also cast as a parameterized decision problem in which, given a graph G and a parameter K, we want to decide whether the graph has a cover S with up to K vertices. Now, the problem has a simple polynomial time 2 approximation, which is tight under the unique James conjecture, that is, there is no 2 minus epsilon approximation. And it is also known to be in FPT, and the best parameterized running time for the problem is 1.273 to the power of K. We use this O star to ignore polynomial factors. And also there is no sub-exponential running time under ETH. And the problem serves as a testbed for techniques in parameterized complexity, which is essentially what we do. And we're going to focus on parameterized approximations. So given some alpha between 1 and 2, we say that an algorithm is a parameterized alpha approximation for vertex cover if given a graph G which has a cover of size K, the algorithm returns a cover of size at most alpha K. And we require the running time to be in FPT, that is some function of the parameter K times a polynomial. However, vertex cover is already in FPT. So what we're really looking for is a trade-off. That is, we want that as the approximation ratio increases, we want the running time to be reduced. Now, vertex cover was previously studied from this perspective, and the existing results include a parameterized alpha approximation for every alpha between 1 and 2, which has a running time of 1.273 to the power of 2 minus alpha, all of this to the power of K. And we have here the base of the exponent, the 1.273 to the power of 2 minus alpha, as a function of alpha is the blue line here. And this can be attained using some preprocessing techniques. And there is also a work by Brankovic and Fernau, which provided 1.5 approximation in time of 1.083 to the power of K, which used some dedicated branching algorithm. And those are the black dots here. Also, the base of the exponent of the running time as a function of the approximation ratio. And what we essentially attain in this work is this red line, a significant improvement over the running time. So we will start with the algorithmic idea, and then the algorithmic idea will lead us to the mathematical problem we needed to solve. And we're going to take a simple branching algorithm for vertex cover and convert it into a randomized branching algorithm. So the algorithm is the following. It's a 1.46 to the power of K algorithm. And it goes as follows. If there is a vertex V in the graph with at least 3 neighbors, the algorithm branch over 2 options. Either the vertex V is in a minimal cover, or if it's not in a minimal cover, in order to cover all the edges adjacent to it, all its neighbors have to be in the cover. So the other option is that the neighbors of V are in the cover. And if no such vertex exists, that is, the maximal degree in the graph is 2, then we can find a minimal vertex cover in polynomial time. And it can be easily shown that the running time of this algorithm is dominated by the recurrence P of K equals to P of K minus 1 plus P of K minus 3. And you get the running time by solving the recurrence. And what we do is, or the basic algorithmic idea is to convert this branching with a randomized branching. So what we do is we fix in gamma and we provide the following algorithm. That is, if there is a vertex V in the graph with at least 3 neighbors, with probability gamma, we will add V to the cover. And with probability 1 minus gamma, we will add 3 of its neighbors to the cover. And as before, if the maximal degree is atmos 2, we just find a minimal vertex cover. Now, this is a polynomial time algorithm, and it truly returns cover of the graph. But we don't know what is the cardinality, how many vertices will be in this cover. And specifically, the question we're interested in is what is the probability that the algorithm returns a cover with up to alpha k vertices, given that the input graph has a cover of size k. And we can formalize this. We can write P of B and K to be the minimal probability that the algorithm returns a cover of at most B vertices. We will refer to this B as a budget sometimes, given that the graph has a cover of size at most K. And we can write this large recurrence. We will go back to it in a second. And it can be formally shown that this capital P of B and K is lower bounded by the small p of B and K. So what is this recurrence? So P of B and K is the minimum over 2 arguments. And for example, the first argument deals with the case in which the vertex B is indeed in an optimal cover. So with probability gamma, the algorithm adds it to the cover. So it reduces its budget by 1 and also reduces the minimal vertex cover size by 1. And with probability 1 minus gamma, the algorithm adds 3 of the neighbors of V to the cover. And then it reduces its budget by 3, but it does not necessarily reduces its parameter. And the second line actually deals with the symmetric case in which the vertex V is not in the cover. And we also have some initial conditions, that is, if the budget is negative, we cannot find a cover of negative size. And if the minimal vertex cover size is 0, it actually means that the graph does not have edges, then we will surely find a cover with a non-negative budget. And this is an intuition, and it can be formalized to prove this lower bound. And so how can we use it? So what we can do is to first can note that this P of B and K can be computed. So we can run our randomized branching algorithm for 1 over P of alpha k and k times. And then we will get an alpha approximation with a constant probability. So essentially what we get is an alpha approximation algorithm, and its running time is dominated by this 1 over P of alpha k and k. And what we want to do in order to understand the running time is to find some constant c, such that P of alpha k and k is roughly c to the power of minus k. And it turned out that there was no known answer for this question. And it essentially diverted our work from randomized branching and algorithm to solving the recurrences, or the specific recurrence. And what we know about recurrences is not a lot. We know how to solve recurrences in a single variable. And the only similar work we found is a work by Epstein from 2006, and it deals with a different class of recurrences with multiple variables. It is commonly used in measure and conquer algorithms. So what are our main results? So first of all, we solved the recurrence. Actually, we took this recurrence, we generalized it into a family of recurrences, and we provide a simple solution for the asymptotic behavior of each of the functions in this family. And for example, if we can discuss the algorithm we've just seen, we can get a 1.5 approximation in time, which is again the inverse of P of 1.5 k and k. And now we can compute it at least for specific value of gamma, and it turns out to be 1.04364 to the power of k. And it is already an improvement over the previous test results. And we use this solution for the recurrences along with the idea of randomized branching, and provided parameterized the approximation algorithms for vertex cover at 3 sets. And those provided significant improvement over the running times of the previous best known algorithms. And some examples are 1.5 approximation in time, which is 1.017 to the power of k. It is actually very similar to the algorithm we've seen. And we also get, for example, 1.1 approximation in time, which is 1.166 to the power of k. And as I said, there are additional results for 3 sets as well. Okay. And are there any questions?
Yeah, thank you. Questions? Counterexamples?
Can I ask the obvious question?
Yes.
Yeah, go ahead.
If you really want to compute vertex cover, let's say you take part in the PACE challenge, would you use your algorithm?
So I'm not very good at programming my algorithms, but at least if you want an approximate solution, then yes, definitely yes, without any doubt. It's completely practical. I think there is some little gap between, I think if you look at it from a practical perspective, you can make it a bit faster because we use this lower bound we use in some sense the worst case lower bound in order to guess how many iterations we need. So you might relax it. Actually, if you actually program it, you just run it as much for the time you have and then you stop. Yes, I think it is usable, completely usable.
So is it kind of, does it give you some kind of heuristics actually? Like, can you use it as a heuristics basically?
I mean,
you know that if you try it on some normal instances, do you get results actually? Just
I've conducted the work from the theoretical perspective, so I never really thought about it in terms of heuristic because you have an algorithm and it's proven to work. So, and my guess is that it will work. So I'm not sure where the heuristics come into play.
Basically about the timing. So in some small time, actually, like you see what you get actually.
So in some sense, what you do here is that you run the algorithm for some amount of time. So I think the main heuristic will be just to let it run for the time you have and not for the time you want it to run.
So is your time analysis actually optimal, or do you know, could it be improved?
The analysis of the recurrences is optimal. The analysis of branching algorithm in general is not necessarily optimal because usually when people analyze branching algorithm, they convert it into a recurrence, and it's a one-direction reduction. You show that the running time is lower bounded by the recurrence, but you cannot show the opposite. And in general, for branching algorithms, the opposite does not seem to be correct. It often seems that if you will use some more in-depth insight, you can improve the running time. So it's the same here. The analysis of the recurrences is optimal, at least to the degree we claim it's optimal. But it may be that the algorithm provides better results. But then we need to replace the reduction to recurrences by something else.
Okay.
Can I ask another question?
Sure.
Yeah.
So you say instead of a 2 approximation, you have a 1.5 approximation, and then you improve the base of the exponent, right?
Yes.
And we know that if you want to have an exact algorithm, you need to be exponential.
Yes.
But it could be that for a 1.5 approximation algorithm, you could do 2 to the root of k.
Okay. So first of all,
do you have any lower bounds on this? Now comes my question. Do you have do you know lower bounds on this?
So there are some lower bounds, not for 1.5, though maybe the existing lower bounds can be extended to 1.5, but up to 1.38 some number, which is the lower bound of vertex cover under p not equals np, you can provide some lower bounds that there's no algorithm in time which is 2 to the power of n to the power of 1 minus epsilon. So it does not exclude the algorithms which are in time of 2 to the power of n divided by log n. That is still not excluded. However, if the problem of finding some sub-exponential time algorithms that provides 2 minus epsilon approximation for the tiniest epsilon you can imagine for vertex cover will be a major breakthrough. It's a difficult problem. So even if you get to the extremes, it's very hard. We're unable to get something which is sub-exponential at the moment, but we cannot prove it or justify it by some assumption or something.
We don't hear you. Tell. We don't hear you.
So I understand you don't have lower bounds for 2 minus epsilon for fixed epsilon.
No, it's an important open problem actually.
Thank you.